Okay, continuing on from where we left off before spring break, we were going to look at this definition here. The sequence of r to the n power is convergent if negative 1 is less than r, less than or equal to 1, and divergent for all other values of r. So let's look at the divergent part first. This means we have to be bigger than 1 or less than negative 1. And that is the graph down here in the blue dots. And as you can see, these blue dots are going to be increasing to infinity, which means they're divergent. When r is less than negative 1, we will be flopping back and forth over the x-axis. And again, these values are getting very, very large or very, very small, heading to positive or negative infinity. So again, divergent, no limit exists. So if we look at where are we convergent, from negative 1 less than r is less than or equal to 1, let's look at this part of the piecewise function when r is equal to 1. So if your base is 1 raised to any power, hence you're going to have a horizontal segment if we connected the dots if it was a true function. So that's convergent. That would give us a limit of 1. If we look at when our values are from 0 to 1, now we have bases that are fractional bases, and we've learned that this is going to decrease as we approach infinity. And if we look at those fractional bases between 0 and 1 that may be a negative value, again, we're going to alternate over the x-axis, but we're still converging to 0, so this would have a limit. So if we look at some examples, if we have r to the n, that just means we're going to increase our powers by 1 forever. R is greater than 1, you can plainly see, that's this example up here, that we're constantly increasing, so there's no limit here, it's approaching infinity. R equals 1, it's always going to be a 1, so your limit is 1. If we're between negative 1 and 1, again, we talked about those fractional bases, whether they're positive or negative, they're going to approach 0 from our graph. And if r is equal to negative 1, we wouldn't want this either, because, again, we're flopping back and forth, but we're never really convergent to anything, so this limit does not exist. So example 10, if we wanted to find the limit using this new definition, looking for the limit as n approaches infinity of 2 to the n minus 2 power over 5 to the n, what we want to do is make these two exponents on your bases to be the same, so we can write a fractional base with the same power. And since our definition says to the n power, let's cut off the minus 2. We all know that when you multiply like bases, you're adding your exponents. So let's factor out a 2 to the negative 2 power from our top power. So that gives us 2 to the n times 2 to the negative 2, which is now a scalar value, which we can move that down to the denominator, call it 1/4, or factor it out front. And there it is. And now both the 2 and the 5 are raised to the same exact variable power, so we can rewrite this as 2/5 to the n power. And so now we know that based off our definition, this limit is going to approach 0. So 1/4 times 0 is a 0. We found the limit. And this converges. All right, we also have what is known as a monotonic function. This is where your entire function is always going to be increasing or always decreasing for all your possible n values greater than or equal to 1, since we're talking about a sequence function here. If at any point in time you have decreasing, increasing, and decreasing, a combination of the two, then your function is not going to be monotonic. All right, so definition number 11 here, a sequence a sub n is bounded above if there is a number, let's say capital M, such that the sequence function, that's your y coordinate if you will, thinking function wise, is less than or equal to this capital M for all your possible n values of your sequence function. It is bounded below if there is a number, let's call it lowercase m, such that that lowercase m, hint hint, y value, is less than all the y values of your sequence function for all your n's greater than or equal to 1. So if it's bounded above and below, then a sub n is considered a bounded sequence. So here's a picture of what we're talking about. Here we have a bounded increasing monotonic sequence. So here is my sequence value starting with n is 1. It's getting bigger and bigger and bigger, and it's starting to level off to the point where it has a limit here at capital L. So that means you are bounded below the first term right here, and we are increasing and bounded above by the limit. So therefore, this monotonic sequence theorem, every bounded monotonic sequence is convergent. It has to converge to some limit. So again, here's that capital M somewhere above all of them. Most of the times what we'll be looking at is the limit, because that's what we will be approaching. The only one we don't want to work with this is, again, if we're bouncing back and forth over that limit, then we may have to have a different different bound up above that contains all those points. All right, so determine whether the sequence is increasing or decreasing or not monotonic. And is it bounded? Well, we can see right away we have alternating signs, so it's not monotonic. So we'll use our absolute value sequence here. We will get rid of the negative base by taking the absolute value of our sequence function. Now we can see as n approaches infinity that this is going to approach infinity as a whole entire function, so therefore it's not bounded. We have nothing bigger than infinity. All right, same thing with example 12. We do have a negative exponent here, so I think what I'm going to do here is I'm going to change that up and start putting in some numbers here, but that negative exponent is going to make me move these negative exponents, e to the negative 1, e to the negative 2, e to the negative 3, is going to make me move that into the denominator. And now I'm starting to get an idea that, hey, this might be decreasing because my denominator is getting bigger and bigger faster than the numerator. But we need to show that. We have to prove that that's going to happen all the time. So one way we can do that is to use the definition of a decreasing function. So what you want to show is that a sub n plus 1, that's going to be the very next term in your sequence, is always going to be less than the previous term. So therefore, you will be constantly decreasing. So if your next term is always less than the previous, you must be getting smaller as you go along. All right? So we take this notation, we put in n plus 1 for every place we see n in our normal a sub n function. So here's the n plus 1 times e raised to the negative n plus 1, and this is our normal a sub n function, n times e to the negative n power. So what we want to do here is we want to try to get a constant value to just one of these two sides. All right? So let's move this, because it's a negative exponent, down below. Then multiply this term to both sides of your inequality. That will get the e's over to the other side on the right side. So base e is now completely on the right side. All right, so I'm left with then just n plus 1, which is pretty close to having a constant here. So what I want to do now is I want to combine the right-hand side, multiply like bases. You add the exponents, so the negative n plus n cancels out, leaving me just e to the first power. I'm going to subtract over the n, and now the right side is a variable expression which is trying to be greater than that 1, or in reverse, 1 is less than this variable expression. Well, we know e is 2.7, so if we have 2.7 minus 1, this is approximately 1.7 times n, and since n is starting at 1, then 1.7 is obviously going to be larger than the 1, so yes, it's a decreasing function. Okay? All right, another way is you can use the first derivative test. If you go back to Calc 1, take the function, take its derivative. We'd have to use the product rule here. E to the negative x times the derivative of x is 1 plus x times e to the negative x. Chain rule times negative 1 from the exponent. Do a little simplifying here. changes the sign. We'll factor out the e to the negative x. And if you recall, you now test these values. Well, e to the negative x for when x is greater than 1 is always going to be positive. Well, I can't put a 1 in here because that would give us a 0, so anything greater than 1 over here is going to give me a negative. Well, a positive times a negative is a negative value. That's less than 0. So that tells us that all your tangent slopes are negative, and therefore you are decreasing. All right, so in summary here, a sub n is a decreasing sequence, so it's monotonic and bounded above by 1 over e. That's our biggest value. That was our very first one. Okay, the limit as x approaches infinity for x times e to the negative x is the same as the limit as x approaches infinity of x over e to the x. By L'Hopital's rule, that becomes 1 over e to the x for our function, which again, hey, our denominator is bigger than the top, so that's approaching 0. So if the function works, therefore so does the sequence function have to have the same limit that we talked about before break. And that's going to be your lower bound. We have a bounded value above, we have a bounded value below. So a sub n is a bounded monotonic sequence. So a sub n converges based off of theorem 12. Other types of sequences, recursive. Terms are defined by previous terms. Example, find the first 7 terms of this sequence. A sub n is equal to 2 times a sub n minus 2 plus a sub n minus 1, where a sub 1 is 5 and a sub 2 is 6. So they've given us the first 2 terms, 5 and 6. All right, now what we have to do is, now we look at this, what happens when n is 3? Well, 3 minus 2, that would be a 1. So that's the first term, 5. So 2 times 5 is 10. 3 minus 1, that'll give us a sub 2, which is 6. So that 10 plus 6 is going to give us 16. So there it is, over here to the right, all worked out. All right, so now we're going to try the next one. A sub 4. We put in the 4 for the n. That's going to give me 4 minus 2. That's a sub 2. That's the 6 right here. 4 minus 1 is a sub 3. We just found that to be 16, so that's where the 16 comes in. So 2 times 6 is 12 plus 16 is 28. Okay, I'm starting to see a pattern here. If you don't, you keep chugging the numbers. I see 2 times the first term plus the next term. 2 times the 6 plus the 16, 28. So I'm seeing 2 times 16 plus 28 gives us the next term. So there it is. If we plugged and chugged, put in the 5 for n. 5 minus 2 is 3. A sub 3 is 16. 2 times the 16 plus 5 minus 1, a sub 4, 28. So 2 times 16 is 32, plus 28 is 60. And we can keep that pattern going. 2 times 28 plus 60, 116. 2 times 60, 120, plus 116, 236. That's a recursive sequence. All the terms are predetermined by previous terms. You cannot just take the 7 and put it into the formula and create that 7th term. A famous Fibonacci sequence is a recursive sequence. You've probably seen this in your science classes. This is the setup. Starts 1, 1, and in this sequence here you add the 2 1s to make the 2. Then you add the 1 and the 2 to make the 3. The 2 and the 3 added together is 5. 3 plus 5 is 8. 5 plus 8, 13. 8 plus 13, 21. And so on and so on and so forth. All right, factorials are also a sequence. There's 2 ways that these are defined. You can start at 1 and count up, if you will, multiplying all the values up until you get to the n, which is an integer, or you can start at n and count backwards by 1 until you get to the 1. And again, we're still multiplying all these integers together. Now, we have a special case. 0 factorial is a 1. Some people say 1 factorial is a special case too. But if I start at 1, I'm already done, so 1 is just 1. If you wanted to simplify factorials, we want to use this concept here of counting backwards to simplify. And what I mean by that is you start with the biggest number to the factorial. It's at 23. and I want to count backwards until I hit 19 on the top. So 23 times 22 times 21 times 20 times 19. Stop! Put the factorial there. These two are exactly the same. 19 factorial on the top, 19 factorial on the bottom. There's no reason to count both these numbers backwards to 1 because they're all going to cancel out. Let's just cancel them all out at once and be done with it. We multiply those four numbers together, 212,520. All right, if they give us variable expressions, don't panic. N plus 2 is definitely bigger than n, so we're going to start counting down by 1. So we start with n plus 2. We subtract 1 from n plus 2. We get n plus 1. We subtract 1. We just get n. Stop. That's your denominator. N factorial over n factorial cancel. There's my two binomials being multiplied together. It's now simplified. Be careful if they throw coefficients in front of the end. I've seen people want to subtract 1 from both of these terms. No. 2n plus 2 is bigger. That starts us off. You subtract 1, and you only subtract it from the constant 2, so that's 2n plus 1. Subtract 1 from the 1 gives me 2n factorial. It's the same as now the bottom. Cancel them out. And those two binomials multiplied together is your simplified answer. All right, which grows faster, n factorial or some k, raised to the n power? Well, let's let k equal 2, and then 2 to the n would be 2 times 2 times 2 times 2 times 2 forever. N factorial will be 1 times 2 times 3 times 4 times 5 times 6, all the way out to wherever n is going to go to. Well, if you notice here, the first four 2's multiplied together is 16. The first four terms, 1, 2, 3, 4, is 24. We are now bigger. Everything before that, 8, 6, 2 to the n was bigger. But at some point in all factorials, you will get bigger numbers being multiplied together. All right, so for n is greater than or equal to 4, 2 to the n power is less than n factorial. So in fact, if this were a limit, since the bottom grows bigger faster than the top, our limit would be approaching 0. So we got to identify where those factorials are. They get bigger faster. If it was flipped, all right, in our next example, now the n factorial is on the top and that's getting bigger faster, then we have no choice but to be approaching infinity. And then that limit doesn't exist. This diverges. Okay, and again, up here when I have this in fact, it doesn't matter what base you have here for k. You could be starting out at 100. 100 times 100 times 100. Doesn't matter. N factorial will eventually pass up the hundreds, and you will get numbers bigger for products than the top.